Students, in this video I am going to go over how to graph quadratic equations, radical functions, and absolute value functions using this technique of transformation of functions. So just to recap what we've covered so far, right? So if, let's say, I have a parent function, I'm calling that y is equal to f of x, and again, whatever I throw in for x, that's what I'm going to have to, evaluate the equation by, okay? So that's our parent function. I can then perform a series of transformation, either moving things left, right, up, down, or applying a vertical stretch or a vertical compression. So all the rules that we had talked about involving those transformations for quadratic functions, okay, they apply for universally to any kind of function, as we had seen in the past couple of assignments. So let's take a look at this guy right here. Okay, we're going to graph this relatively quickly because we have an understanding of how to approach this. So this is, I immediately am able to pinpoint what the vertex is. This is located at 1, 2. So this is going to be my vertex right there. And this is going to have the parent function is going to, there's no vertical stretch, so therefore it's going to look like this. I'm sorry, I made a mistake. That's what happens when you're talking by yourself, well, talking to yourself. So it's 1, 2. I graph 2, 1 there. So it's going to look like this, and then it's going to look like that. So how am I able to get this really that quickly? Because, again, in the parent function, okay, what was the parent function again for y equal to x squared? So it was -2, -1, 0, 1, 2. So it was 4, 1, 0, 1, 4, right? So therefore, this is going to be spaced 1 apart. This is going to be spaced 4 apart, okay? So that's pretty much a picture that you're going to have to, I hate to say this, but, memorize or be familiar with at least. Okay, so let's do second question here. We're going to dilate by a factor of 2, and we're going to move the points 2 to the left and 3 down. So 2 to the left and 3 down. So this is going to be my vertex. So the points are going to be dilated by 2, which means I am going to end up with this dilation, right? So the next one is going to be 8 away from this. So this is going to be 2 away, and the next point is going to be 8 away. So 2, 4, 6, 8. It's going to be here. And then the other point is going to be over here. Again, you can always resort to just plotting points in, okay? So for instance, you can throw in, let's say -3, okay? Let's say you didn't know that the point was supposed to be located there. You can then figure out what that is by performing the computation. And then again, you can do this one more time for -4. If you throw that in there, okay, you get -2 squared, which is 4. 4 times 2 is 8. 8 minus 3 is 5. So that's how I'm able to end up with 5. But again, you don't have to go through this route, okay? If you have the picture memorized, okay, if you have that pattern like internalized, okay, you can go about this much faster, more efficiently, okay? So next is I have x plus 4 squared minus 2. The vertex here is located at -4, 2, which is this point right here. There's no vertical stretch, so it's going to just look like this. Let's take a look at the next one. Here there is going to be a vertical stretch, and there is going to be a flipping action as well. The vertex is located at 2, 3. So 2 and then 3 up, so it's located here. This is going to be an upside down parabola, so I know the shape is going to look like this. So this is going to be 2 apart, and then the next one is going to be 8 apart, right? 2, 4, 6, 8. So it's going to be over here. Again, if doing this is, if you're not comfortable doing what I just demonstrated over here, you can also throw in values of x that are 1, right? What are you going to end up with? 1 minus 2 is negative 1. Negative 1 squared is 1. So I have negative 2 plus 3. It's going to be positive 1. And then you're going to do it again for, let's say, 0, right? If I throw in 0, I get 0 minus 2 is negative 2 squared. That's positive 4. Positive 4 times negative 2 is negative 8. Negative 8 plus 3 is negative 5. So that's how I end up with negative 5 there. Again, you can do that, okay, to figure out all the different y coordinates as well. But again, try to use the technique that I just showed you where you can, sort of just draw this out, okay, based on transformation of these functions here. All right, moving on. Square root of x plus 4, right? So square root of x plus 4, this is going to, again, the parent function is, it looks like this. I'm just going to use these 3 points as my main reference, okay? I'm going to be shifting this up. So I'm going to change color here in blue. I want to make it a little thicker. So this is going to be the vertex is located at 0, 4. So there you have it. This is going to be my function. Let's try it again. Let's not do that one, just because it's very, very similar. There's no vertical stretch or compression happening with this example, so which is okay. The vertex is located at negative 3, 4. Okay, so negative 3, 4 is over here. That's my vertex, and it's going to take on the same shape. So this is going to be the function. But if you're not comfortable doing this, okay, you can also substitute in values, okay, to generate the y coordinates. Let's go through the next one. Let's not do that because it's very, very similar. Actually, yeah, let's not do that. Let's do this guy right here. Okay, so I have absolute value, negative 2 times absolute value of x minus 4, and then subtract by 2. Immediately from this, I know that the vertex is located at 4, negative 2. So 4, negative 2 is located over here. I'm going to have a dilation of negative 2. Remember, okay, the parent function looks like this, right? It's a v. So if I'm dilating it by a negative 2, then that means they're going to be spaced 2 units apart. So that means I'm going to end up over here. It's a dilation of negative 2. Let's take a look at the next one. Okay, this is a dilation of positive 3. Okay, so I want to move 3 units to the left and 3 units up, so it's going to be over here. That's my vertex. Because I'm dilating by a factor of 3, remember the original parent function is located over here. So we're going to be multiplying by 3, so that means the next coordinate will be located over here. If I wanted to figure out the other coordinate to the left and right of what I just drew here, it's going to be 3 more units going up that way, right? Anyway, that's going off the grid then, but that's the graph. Okay, we're not quite done yet because the I went a little ahead. I forgot to read the instruction at the very beginning. It says also the state, the domain, and range, right? So I haven't done that in the videos where I graphed out the quadratic equations, but having gone through talking about domain and range in the previous video on when I discussed going over square root functions, the domain and range, what the domain is, what values of x can I substitute in here to evaluate the function with? So the domain for this guy whoops, is x is, well, I can throw anything in here, right? There's really no limitation. So because of this, it's all real numbers. What exactly is the range? I see here that I do have a minimum. That's the lowest y-coordinate. So because of that, the range is going to be greater than or equal to 2. Let's take a look at the next one here. Because I can throw anything in to evaluate a quadratic function, the domain, one more time, is x is all real number. And as a matter of fact, the domain for any quadratic equation is going to be all real numbers. The range, okay, here is going to be y is greater than or equal to -3. Let's do this one here. Here I do see that we have this time it's not a min, it's a max, right? So like I said before, the domain is still x is equal to all real numbers. The range, it's dependent on where the vertex is. So now the range is going to be y is less than or equal to 3, because all the y coordinates are going to be below 3. Let's take a look at this guy. So the domain is x is greater than or equal to 0. The range is y is greater than or equal to 4. It's dependent upon what that vertex is, right? Okay. This guy right here, the domain is x is greater than or equal to -3. The range is y is greater than or equal to 4. The domain, there's really no limitation, okay? Just like with the quadratic equation, there's no limitation as to what we can throw in for x to evaluate absolute value. For that reason, absolute value functions have domains that are all real numbers. So when we evaluate linear absolute value equations, that is, like this in here is a linear form, right? So linear absolute value equations, the domain is all real numbers. And then the range, very similar. If you look at this, what I have here, that is a max. So therefore the range is y is less than or equal to -2. And lastly over here, the domain, one more time, is x is all real numbers. And range, here I have a min, so y is greater than or equal to 3, because that is the minimum y coordinate.